Okay. Item B, intrinsic geometry, exterior algebra in 3D. This case, for instance, is 1D, it's 2D in this case here, 2-dimensional. B, part 2, lecture 9, Jacobian of the transformation between bases. Now, consider the Euclidean spaces and the respective chain rule. Now, transformation from polar to Cartesian. You see, this is r theta, these are variables. These are variables belongs to the Cartesian. So x is r cosine theta, y is r sine theta. Now a vector belongs to the, in this case, to the polar coordinates, is transformed, is mapped by the push forward, you see, to yq, where xp, for instance, these are the components of this vector, and this is xr partial r, x theta partial theta. This is yq, you see. Now, I want the transformation only between bases, only, not components, you see, between bases. So, 1, from polar to Cartesian basis transformation. Now, x r cosine theta, y r sine theta. We want to express this basis, partial r, partial theta, in terms of this partial x, partial y. This belongs to the Cartesian, and this belongs to the polar. Now, from calculus, the differential of a function, you see, is a partial derivative respect to x dx plus partial derivative respect to y dy. This implies, attention now, chain rule, partial respect to r. You see, partial d of dr is partial respect to r. This is partial x respect to r, partial dx. This is partial y respect to r, partial dy. But this over here, you see, partial x respect to r is cosine of theta, and partial of y respect to r is sine of theta. You just substitute it from here. Now, then I express this basis, partial respect to theta, which belongs to the polar coordinates. This is partial x respect to theta, partial x, partial of y respect to theta, and so on. Attention now, the chain rule. This is minus r sine theta. You see, when we derive partial x respect to theta is minus, because derivative of cosine is minus sine. Likewise, this r cosine theta. This is x and this is y. Now, easily you can relate this. The basis belongs to the polar coordinates, to the basis belong to the Cartesian. I call 1. Now, I repeat, x, y, partial x, partial of y belongs to the Cartesian coordinates. You see, they are on the right-hand side. See, because I want to calculate the basis in polar coordinates. Now, the same procedure. Now it's from Cartesian to polar. Now, you see, we want now the basis belongs to the Cartesian in terms of the base belongs to the polar coordinate. Again, the differential of a function I can express, okay, in terms of coordinates r, in fact. Again, partial derivative x, this partial derivative of x, they belong in both. Likewise, partial respect to y, partial respect to y, partial respect to y, clearly. Now, since Rx is r cosine theta and y is r sine theta, remembering that r is a square root x squared plus y squared, and theta is the inverse tangent of y over x. Now, the problem here is just doing derivatives, okay? So, partial r respect to x is just x divided by r. You see, you just follow here easily. This x divided by r is cosine of theta. Likewise, partial r respect to y, same. This is b y of r sine of theta. Now, partial of theta respect to x. Remember, theta is tangent minus 1, is the inverse of y over x. So, from calculus, you take the derivative here. This leads to minus r sine theta divided by r squared. Likewise, this partial derivative here, you see, is x divided by x squared plus y squared, which is x divided by r squared. Now, we obtained, you see, the relation between given polar, I get the Cartesian. You see, this is the opposite. Okay, I give the Cartesian, okay, and obtain the polar. I call 1 and 2. You see, this is 1 and 2. I define the Jacobian, okay, this matrix over here. So just copy from here, attention now, to there. Comparing, you see that this is the inverse Jacobian. The inverse of Jacobian is just the elements, okay, of this expansion here, expressing here. You see, you just copy from here to here. So this inverse the Jacobian. You see? So if you apply this over here in 1, I'll get the polar basis. If I apply the inverse, okay, if I apply this, then I get exactly this partial derivative over here. That's why this is the inverse of this. Okay? That's it. That's quite clear. See? Just from calculus. See? And the chain rule, differential of a function, in this case, it's 2-dimensional. Okay? That's it.